Hello everyone, welcome to my presentation about semantic labeling-based vehicle detection in aerial imagery. In recent years, deep learning-based detection frameworks also achieved top-performing results for vehicle detection on aerial images. For this, high-resolution feature maps are required for an accurate localization and classification of tiny objects, such as vehicles, and therefore shallow layers of standard models like WACV18 or small networks are applicable in order to provide a sufficiently high feature map resolution. However, the low degree of semantic and contextual information can result in a high number of false alarms, as shown on the right. Objects with shapes similar to vehicles are misclassified and result in false alarms. And we proposed two multitask models that combine the detection task and semantic labeling task to overcome this drawback. The first model is called implicit multitask faster RCNN and is an extension of faster RCNN by an additional semantic labeling branch, which is shown on top. It's the detection branch, and the lower branch is the semantic labeling branch. Therefore, we used a dilated convolutional architecture. And both the detection and the semantic labeling branch are based on WACV18 and share the first 4 blocks of convolutional layers. And for training, we use the joint multitask loss, which is comprised of 5 losses, 1 for the semantic labeling and the 4 losses of faster RCNN. And then we also extended this model, and for this, features of the semantic labeling branch are explicitly used as additional feature map for detection. And for each object proposal, an additional region of interest pooling layer extracts features from the semantic labeling branch, which are then also used for the classification. And the feature of both region of interest pooling layers are combined by element-wise addition, as shown here. And for evaluation, we use the ISPRS Semantic Labeling Challenge Potsdam Dataset, which is comprised of 38 patches with a resolution of 6K times 6K pixels and has a ground sampling distance of 5 centimeters. And labeled ground truth is available for 24 of these patches, as well as bounding box annotations for category car are available. And here are some results shown. As baseline, we use faster RCNN and some extensions of faster RCNN. And what we can see here is that using semantic information results in an improved detection, results. And the EMT faster RCNN exhibits the best error precisions. And the reason for this is the clearly reduced number of false positive detections. For instance, for EMT fast RCNN, the number is reduced by 58.8% compared to the original faster RCNN. And if you take a look at the runtimes, EMT faster RCNN and faster RCNN exhibit identical runtimes, as the additional semantic labeling branch of EMT faster RCNN can be disabled for deployment. And the computation of the additional feature maps in case of EMT fast RCNN results only in a slightly increased runtime. We further did some ablation experiments to analyze the both branches, especially the semantic labeling branch. For this, we evaluated different semantic labeling architectures, and we also applied our models on different ground sampling distances to analyze how it performs for different vehicle sizes. And our EMT fast RCNN clearly outperforms fast RCNN for all GSDs. And finally, I will show you some qualitative results. The top row shows results of the original faster RCNN, and the middle row shows the semantic labeling mask generated by the EMT faster RCNN, and the bottom row the results of the EMT faster RCNN. And what we can see here is that the number of false positive detections caused by vehicle-like objects is clearly reduced. For instance, if you take a look at the left image, the detection on the building is not detected anymore. Yeah. Thank you for your attention, and for more information, please come to my poster.